Hello again. In this video we're going to look a little bit more carefully at the idea of a derivative, exactly what it is, what it means, and we're going to look at it with this very specific example that I will get to here in a minute. If you missed the first video, the video right before this one, I went through this picture fairly extensively, what the slope meant, really what all these numbers mean. So if you missed that, you might want to go back and watch that first and then come back and watch this one. Okay, what we want to do is we want to confirm with calculus what we know from this picture. In other words, what the geometry is telling us. Right now we know that the slope of this secant line represents what? The slope of it represents a distance, this is my rise, a distance traveled divided by the time it took you to travel that distance. Okay, remember this equation is describing an object that's being thrown straight up into the air with an initial velocity of 100 feet from a height of 10. So what this slope represents is the average velocity of this object in between 1 second and let's put it to 3 seconds. Okay, so the average rate of change roughly is 35.82 feet per second. Okay, in the previous video what we did was we looked at what happens if this time frame slowly closes in on 0. And you can see that my line is no longer a secant line, but it looks like it's trending towards a tangent line. Okay, well the slope of that tangent line still has the same representation as the slope of this secant line. The only difference is the slope of this tangent line here represents an instantaneous velocity. In other words, the velocity of this object when time equals 1 in this particular example. Okay, I could figure out what's the instantaneous velocity at 2. I just put both of my dots at 2 and I would have to calculate the slope of that tangent line there. Okay, and you can see that the slope at this point is 36.26 feet per second. Now that should make sense, because what is happening to an object as you throw it straight up into the air? Well, as you throw an object straight up, I would hope your intuition would tell you that it starts to slow down because of gravity. So notice the velocity here is 67.63. The velocity at 2 seconds is 36.26, and the closer we get to the top, you could probably guess that the closer our velocity is getting to 0. Okay, and this should make very good sense now, because when the object is at the top, when the object's actually at the top, we're going to get a horizontal line. Now this is just going to be kind of an estimation here. I'm trying to get it close, but if I get it close enough, it looks like, this is a little bit hard to do, I apologize. Well, that's close enough. Anyway, you can imagine that the slope of this tangent line, if it was truly horizontal, would be 0. Okay, well let's try to confirm with calculus what this geometry is telling us. Okay, the geometry is telling us here in this picture that our instantaneous rate of change at 1 is right around 67.97 feet per second. So let's go try to calculate this now. Okay, well how do you do that? Well, we have to use the derivative. And what is the derivative? Remember that the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. Now I want to drive this home, that this numerator represents the distance traveled in our particular example. Okay, let me spread this out again. F of x plus h, here it is right here, f of x plus h minus f of x equals 62. What did I just do? I took the height of this green ball, 155, I subtracted from it the height of this red ball, 93.36, and I get this distance right here, which is 62. Okay, well, divided by what? We're going to divide by this length of time. Well, this length of time is simply h. If this is x, then this point right here would be x plus h. Okay, well, for our particular example, our x equals 1. So I can actually write the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. Okay? So now let's go ahead and evaluate this what we call difference quotient. Okay, so how do we do that? Well, wherever I see an x in my function, I'm going to first replace it with a 1 plus h. Let's go ahead and do that. To minimize my mistakes, I like to make what I call skeleton equations. And all I mean by that is wherever I see my variable, I replace it with some parentheses, and that way I can come back and make a substitution and lessen my chance for making a silly little error. So now, here's my function, and I'm going to evaluate f of 1 plus h. So I simply insert 1 plus h for my input. In both locations, this is where x used to be. So this whole thing right here represents f of 1 plus h. Okay? Now, we're going to subtract from that. We're going to subtract from that f of 1. What is f of 1? Well, it's important that we start with some parentheses here because I'm going to be subtracting all of f of 1. And f of 1 is simply going to be negative 16 times my input squared plus 100 times my input plus 10. Okay, and my input is 1. Okay, and I need to close my parentheses here. Okay, so this right here represents f of 1. Okay, and this right here again represents f of 1 plus h. Now, this is all divided by, it's hard to make a straight line, all divided by h. Now, all that is left to do is to crunch this algebra. Okay, so let's go ahead and start doing this. The limit as h goes to 0 is negative 16, or I should say of. If I square this, I should get 1 plus 2h plus h squared. And then I'm going to distribute this 100 through, and I get 100 plus 100h plus 10. Okay, minus all of this. I don't care how you do this. You can come in here and crunch all this if you want. This will be 110 minus 16, so it looks like we have a minus inside the parentheses there. 110, what would that be? 94? It would be 94. Okay, all divided by h. Okay, well, going further with this, we have the limit as h goes to 0 of all this stuff right here. Now I can start to distribute my negative 16. This will be a minus 32h minus 16h squared plus 100. Actually, I could even do I could do 110, can't I? Okay, so 100 and this 10, and this actually minus 94 is going to be, what would that be? That'd be 16? Positive 16. Okay, all, whoops, I forgot this 100 plus h here. There's my numerator. All over h. Okay, moving on. Now some of these steps, I know some of you are probably skipping some of these steps and you're getting to the end before I am, but I just want to make sure you see every little step. Well, look at this. I have a negative 16 here. I have a positive 16 here, and those go away. That's just 0. So up top, also notice I have a negative 32h and a positive 100h. I can combine those to get a positive, well, let's do the negative 16h squared first. I will get a positive 68h all over h. Okay, well, if you look at that very carefully, you'll notice that you can reduce an h out of everything. You can reduce an h out of the top. You can factor an h out of here. It cancels with this guy down here, and you're left with the limit as h goes to 0 of negative 16h plus 68. Okay, well, this looks like a very easy limit that we worked on several videos ago. I can just go ahead and use direct substitution. Substitute 0 in for h here. This goes away, and I'm left with 68. Now, don't forget what we're doing. What are we doing? What does this represent? It represents an instantaneous rate of change, and in this case, it's in feet per second. Now, if you've forgotten what we estimated it to be, the geometry said that at 1, that the slope of that tangent line was very close to 68. You can see I get 67.97 right there. Okay, so it looked like the derivative worked out just fine for us. Again, all we did was we evaluated this difference quotient, okay, for x equals 1, and the rest was just a bunch of algebra until we got a final answer of 68 feet per second. Remembering that this is an instantaneous rate of change when time equals 1. Okay, so I hope that made sense. Look for future videos to do even some more examples with the derivative and applications of the derivative. Thanks a lot.